we're going to power through some examples. Really, that's what this section is all about, just examples over and over of using these kinds of things. And let's start with, this is example 3 in the book, and we are going to fabricate a box. And for my students, this may look like a familiar problem. We did a similar one, but without the calculus in Algebra 2. We're going to take a piece of steel, cardboard, whatever, and we're going to cut corners out. And the corners are going to be x by x. The sheet of metal started out as a 25 by 20. And the question is, how can I maximize the volume of this box? Well, here's what we know. We know that when we make this box, that the height is going to be x, that the width is going to be 20 minus 2x, and that the length is going to be 25 minus 2x, which means that the volume of this box is x times 20 minus 2x times 25 minus 2x. And we can also specify that the domain of x has to be between 0 and 10. We can't cut out less than 0. We can't cut out more than 10 because we run out of space in the box here. So if you think about our strategies, we drew a picture, we defined a variable, we read the problem carefully, blah, 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 and we're trying to maximize volume. This is everything we need to know. So I'm going to multiply out. I could theoretically take the derivative of that, but it's an awful lot easier in this case to multiply out and write this as a cubic. And there's my cubic. Just as an aside, if you have two things, sometimes it's easier to just use the product rule versus multiplying. When you have 3, it's a lot easier to multiply it out, at least for a straightforward polynomial. So the derivative, the rate of change of volume with respect to x, is 12x squared minus 180x plus 500. And I know that extrema can be found at the endpoints or the critical points. So let's start with the critical points. The derivative is equal to 0. I could get fancy and do all the math, or I could just plug this quadratic into my quadratic formula. I actually have a program on my graphing calculator, which is pretty easy to write. And what it tells me is that I will get x approximately 3.681 or x approximately 11.317. And my endpoints, of course, are at x equals 0 and x equals 10. So I need to analyze these. Well, one thing I might notice is that that right there is not in the domain of my function, so I can cross it off. So therefore, my choices are the volume at x equals 0, the volume at x equals 3.681, and the volume at x equals 10. What I know is that this is 0 and this is 0 because I've either cut nothing out of the corners, which means I have a flat sheet of steel, or I have cut everything out of the corners and I have a vertical piece of steel of double thickness. And that means that this must be a maximum, since it starts at 0, goes up, reaches an extrema at 820, goes back down again. I could do second derivative tests, but honestly, in this case, I don't really need to. It's a straightforward, simple problem, starting at a minimum, ending at a minimum. Therefore, my critical point must be a maximum. Interpretation. This is a very important part of a calculus problem. I need to explain what exactly I just found. The maximum volume of 820.588 cubic inches will be found when I cut out 3.681 inch squares. All right, for my class, why don't you go ahead and pause, do exercise 7 out of the book. Sorry, stylus just quit working. Reset, do exercise. Stylus still not working. What's going on here? Why? There we go. Do exercise 7 out of the book. Next example. Let's design a can. Example 4. Designing a can. Here's what we are told. We want a 1 liter oil can. It is designed as a right circular cylinder. And we want to minimize the material use. So let's analyze this. Useful information, 1 liter oil can. We should know that 1 liter is equal to 1,000 cubic centimeters. If you don't, you do now. File it away in those memory banks. A right circular cylinder, so I'm going to go ahead and skip forward to making a drawing of the situation. Right circular cylinder will have a radius and a height, and minimize the material use. So minimize, critical point again, material use. So a couple interesting things here. First of all, material use means I'm interested in the surface area. And surface area of a right circular cylinder can be found by adding the top and bottom, pi r squared twice, to the can walls, the cylinder walls. Well, the cylinder walls can be found by taking the circumference of the cylinder and multiplying it by the height. So that's what I want to minimize. I want to minimize this. Now, notice that I have 2 variables, r and h, which means I need another equation because I've got 2 things that can change here. Well, 1 liter is a volume, and I know that volume of a right circular cylinder is equal to the area of the base times the height, and I know that in this case this is equal to 1,000, which means that h is equal to 1,000 over pi r squared. Going back to my area equation, I can now rewrite this in terms of a single variable. 2 pi r times 1,000 over pi r squared. Little simplification, the pi's go away, one of the r's goes away, and I'm left with 2 pi r squared plus 2,000 over r. So, minimizing, let's start solving. The derivative of a with respect to r is, well, 4 pi r minus 2,000 over r squared. I'm not sure how I got that. Think about it a little bit. Hint, I rewrote r on the denominator as r to the -1 and used the power rule. And I want this equal to 0 to find those critical points. Multiply everything by r squared. I get 4 pi r cubed minus 2,000 equals 0. And solving for r, I get r equals the cube root of 2,000 over 4 pi, which is approximately 5.419 centimeters. Is this a minimum? Well, let's, in this case, do the second derivative test, just because we have it. The second derivative of this function is 4 pi plus 2,000 over r cubed. And the reason I say let's do the second derivative test is because it doesn't actually require us to do any calculations. I could have plugged in some number less than 5, some number greater than 5.419, done those calculations, but let's say I don't have a calculator. Let's say I'm just doing this, so far there's nothing on here that I've needed a calculator for except, well, I take that back. Okay, I had to find the cube root of 2,000 over 4 pi. But just looking at this second derivative, 4 pi is a positive. And since r has to be positive, you can't have a negative radius, that means 2,000 over r cubed must be positive, which means that for all possible values of the radius, this has to be a positive number, which means that this is in fact a minimum value. So what have I got here? I have a radius of 5.419 centimeters. I'm doing a quick calculation of the height of my can by plugging that back into my equation for the height. I get a height of 10.839 centimeters, which means that the least amount of material needed to make a 1-liter can will result when the radius of the can is 5.419 centimeters. The height is 10.839 centimeters. All right. And you may notice that that's sort of, in terms of right cylinders, 10.839 and a diameter of about 10 point, oh, well, would you look at that? 5.419 doubled, 10.838. In other words, a square. All right, go ahead and do exercise 11, and we'll be back with the next example. So we're going to do some examples from economics, and in this case, we are going to have to do a little setup. We've got to define some terms that we haven't seen before. So we're going to define R of X as the revenue derived from X units. We're going to define C of X as the cost from X units, and we're going to define the profit for X units as the revenue minus the cost. All right. So what do we know about maximum profit? Well, we know that maximum profit has to occur when P of X equals 0. I said that wrong. The derivative of P is equal to 0. We're talking critical points here. Could have endpoints, but since our endpoints in a situation like this, 0 less or equal to X less or equal to some infinite number, obviously you're not going to have max profit at 0 unless you have a really, really bad business model. And then, of course, you can't. There's no maximum number of units you can make. So we will double check to make sure that it's a maximum, not a minimum. But we're going to assume that that maximum will have to occur if it occurs at a critical point. So let's think about the derivative of profit. Well, P prime of X equals, well, since P of X equals R of X minus C of X, we can conclude that using the difference rule, the derivative of profit is equal to the derivative of revenue minus the derivative of cost. And if I set that equal to 0, we discover that the maximum profit will occur when these two quantities are equal. So let's talk about these quantities. The rate of change of revenue with respect to X is called the marginal revenue. The rate of change of cost with respect to X is called the marginal cost. And one way to think about these is what happens at the margins. So for example, if I am making 100 units per week, what happens if I increase to 101? This is where we often look at the idea of marginals, is we say, well, look, I want to increase my production. What's going to happen? What's my rate of change to go from 100 to 101? What does it do to my revenue? What does it do to my cost? And we'll come back and we'll talk about that a little bit more. And then, of course, the rate of change of profit with respect to units is called marginal profit. All right, so let's look at an example. Example 5. My revenue model is defined by 9 times the number of units that I make. My cost model is defined by x cubed minus 6x squared plus 15x. And we will define x in thousands of units. Typical for business to define our variables in terms of thousands, hundreds of thousands, millions. So to maximize profit, we need r prime of x, the derivative rate of change. Well, let's just refer to it as the marginal revenue. Well, we know that's 9. The marginal cost is 3x squared minus 12x plus 15. And we want those to be equal. So 3x squared minus 12x plus 15 equals 9. Simplifying that, we can set it equal to 0. 3x squared minus 12x plus 6 equals 0. And again, I'm just going to use my quadratic formula. I'm going to plug it into a quadratic formula program. I get that I have a critical point at x is approximately 3.414 units, or 3,414 units, and I have a critical point at approximately 0.586 units, 586 units. Don't know where that came from, but there we go, 586 units. So the question is which is a maximum and which is a minimum? Do we have a maximum and a minimum? We must have something going on there. So let's find out. Marginal profit, defined as marginal revenue minus marginal cost. So we've got 9 minus 3x squared minus 12x plus 15. Which is negative 3x squared plus 12x minus 6. The second derivative, and by the way, this is sort of important because when we look down here, we had a positive quadratic, and it might have been easier to say, well, let's just take the derivative of the positive. But that positive quadratic is backwards when we're talking about the marginal profit. So we need to make sure that we actually go back and rewrite the marginal profit, because that changes the derivative to negative 6x plus 12. And what I notice then is that the second derivative of 3.414 is going to be less than 0, making that a local maximum. And that the second derivative of profit evaluated at 0.586 is going to be greater than 0, making it a local minimum. And again, you don't actually have to do this calculation. I looked at this and I said, well, 6 times 3 is 18. Negative 18 plus 12 got to be a negative number. 6 times a half is 3. Negative 3 plus 12 has got to be a positive number. Save yourself time when you're doing these problems, because we're not interested in the value. We're interested in the sign of the second derivative. So Interpretation. Interpretation. To maximize profit. Make 3,414 units. Why don't you do exercise 22 out of the book? And we'll be back with one more example for this video. All right, minimizing average cost. Minimizing average cost. Sometimes you want to minimize your costs. You could make nothing, but if you want to stay in business and the goal is just, hey, you know what, we need to minimize costs right now. We've got a lot of money going out. Maybe we're not worried too much about maximizing profit as we are about just not spending more. And so let's define a couple terms. First off, we've already seen C of X, which is the cost of producing X units. The average cost per unit, therefore, is just going to be that divided by the number of units. This is going to be the average cost of producing X units. So what do we know? Well, we know that we want to minimize average cost, so we want the derivative of C of X divided by X equal to 0. That's going to be a critical point, so let's go ahead and take that derivative. We're going to use the quotient rule. And hopefully you're pretty familiar with the quotient rule, but I'll go ahead and jot down the details. U is equal to C of X, V is equal to X. The derivative of U is C prime of X, also known as marginal cost. The derivative of V is 1, which means that the derivative of average cost is V du X C prime of X minus U dV, 1 times C of X, divided by V squared, and I want that to be equal to 0. Well, in order for that to be equal to 0, then X C prime of X minus C of X must equal 0. Adding cost, dividing by the number of units, I get that the marginal cost must be equal to the average cost. If I want to minimize my average cost, I have to make that average cost equal to the marginal cost. All right, so let's do a quick example. My cost function is x cubed minus 6x squared plus 15x, where x is measured in thousands of units. And I want to find a production level to minimize. Production level to minimize. Whoops. Level to minimize average cost. Guys, by the way, when you're taking notes, when you're writing things down, jot these down, because there's a reference when you see the words minimize average cost. Oh, hey, how do I do that? I set marginal cost equal to average cost. Boom. Done. Moving on. You know how to do the problem. All right. We want to minimize average cost. So, first of all, we need to know the marginal cost. Well, we know that's 3x squared minus 12x plus 15. The average cost, C of X divided by X, is, and I'm going to do a straight up simplification, X squared minus 6X plus 15. And I need to set those equal to each other. 3X squared minus 12X plus 15 equals X squared minus 6X plus 15. Doing a little combining, we get 2x squared minus 6x equals 0. I could do this one in a quadratic formula, but on the other hand, why would I bother when it's that easy? Production level to minimize average cost. I either produce nothing or I produce 3,000 units. Well, if I'm not producing anything, I don't have a business. What this tells me, if I really go back and think about this, is that this problem doesn't make sense unless x is greater than 0. It is a pointless problem if I'm not producing. So the domain of this function, the domain of a production function, is always going to be x greater than 0. As soon as I get to x equals 0, well, I don't even have a business anymore. Why am I doing calculations? Question that we have to answer ourselves, however, is this a maximum or is this a minimum? Well, average cost is x squared minus 6x plus 15. The derivative of the average cost was 2x minus 6. The second derivative of the average cost is 2. 2 is greater than 0. And if the second derivative is positive, then in fact, I have a minimum. Interpretation, if I want to minimize the average cost, I need to make 3,000 units. Why don't you go ahead and do exercise number 25. That's the end of this video and the end of this section. So I'll be back with a section recap. Thanks for watching and hope you learned something.